and a certain conjecture about it. And let me just, because it's a short talk, jump right into it. And hope that at the end of the talk you will see what this conjecture is and why it's hopefully a wrong conjecture. So yeah, here's the outline of my talk. First I will tell you what this conjecture is that I'm talking about here. The idea is basically the two simple properties. One is a compositional property and the other one is a dynamical property, bring you more or less to quantum theory. In the second part I will show you some evidence for this conjecture, which somehow tell you that if you have two ball state spaces, then this already gives you quantum theory. And in the third part, I will speculate about possible counterexamples, why that would be interesting, and how they would be related to interaction between three or more systems. Okay, so what's this conjecture about? Well, the starting point is basically the same as Giulio's starting point, though a bit of a different flavor. It's this framework of convex operational theories. And the idea is to formalize certain laboratory situations, certain processes. For example, processes like this, where we have preparations, transformations, and measurements. And I will skip most of the details of this framework since I'm really using only a tiny little bit of it. In particular, the most important notion that I'll be using is that of a state. So a state here is really whatever comes out of the preparation device when I press the button. Formally, you would say a state is mathematically described as an equivalence class of preparation procedures, where you see two preparations are identical if everything that I do later gives me the same outcome probabilities for measurements. So in Giulio's notation, actually, this would be one of these processes, omega, which have a trivial input and some outgoing system. Okay, now we have single states, but we can also collect all possible states into state spaces. So a state space, and I denote this by a capital omega, is just the set of all possible states that we can have on some given physical system. Now, there are two special cases that you're all familiar with. One of them is just classical probability theory, or CPT here, where the states are just probability distributions. So the state space over n outcomes, say omega n, would just be all these vectors with entries p1 to pn, which are probabilities and sum to 1. In quantum theory, you have a bit of a different state space. You have superpositions of these alternatives, which basically gives you the density matrices, the n by n complex density matrices. But in general, you could have any kind of state space. So here's a bunch of examples. In this framework, actually every compact and convex set in some real vector space is a possible state space. And one famous possibility is what's called the quantum bit or a quantum two-level system. So if you think of a quantum bit in the usual way, you would say you have two states, two orthogonal states, and you have a superposition of the two. And then the superposition can always be parametrized, and most of you will know it. Let me just write it down maybe once again. By two angles, so you can write it as cosine theta over 2 of 0, and then some sine, and some e to the I phi, so it would be a state. And so you see that there are two angles that parameterize a state. And so you can basically depict the state space as a ball here. The pure states are the surface of the ball, and the mixed states are in the interior. Now, a classical bit would look like this. This is a classical binary alternative system. So maybe you have a coin, and you could have heads or tails, or statistical mixtures of these two alternatives, which gives you this line segment, basically. Three-level system would have these three alternatives and the statistical mixtures. So classically, you have something like a simplex. Quantum theory, it looks more complicated. It's quite interesting to see what the quantum three-level system looks like. So this picture is from a paper by Tsikovsky. He tried to depict the 3x3 density matrices, and this is a quite complicated convex object that you get. It's like an 8-dimensional beast with like lots of symmetry, but also flats in the boundary and all kinds of weird features. But in general, in this framework, your state space could just look like any convex set. Okay, so here's a more formal definition. That's what some of you will know in the context of linear ordered vector spaces or order unit spaces. It's actually a set of unnormalized states. So these are the normalized states in the pictures, but in general, with unnormalized states, they will be closed, convex, pointing and generating cones in some finite dimensional vector space. You can also formally define what transformations and measurements are. I will just not do that here because it's a short talk. I want to keep it simple. But yeah, this goes back to also what Julie explained earlier on. Okay, now let's look a bit more at transformations. What is a transformation? Well, a transformation is something where a state comes in and a state goes out. So it maps, it's a map that maps a state to another state, and it should respect mixtures, statistical mixtures. It means it must be a linear map. And we call that reversible in the same sense as Julio did, namely, if it has an inverse, and the inverse is also a transformation. So in quantum mechanics, these would really just be the unitaries. You take a density matrix, you conjugate it with some unitary matrix. In classical probability theory, you basically take your probability vector and you permute the entries. These are the classical reversible transformations. Now, if you look at the geometry of your state space, then a reversible transformation maps that state space into itself. So it must be a linear symmetry of it. For example, in the quantum case, in the qubit, this takes the Bloch ball and just rotates the Bloch ball. And they always map pure states to pure states. Okay. Now here's one thing that, one of two properties or postulates that we'll be interested in the following, and that's called the reversibility postulate. It's somehow a very natural property of state spaces. It says the following, it says that for every pair of pure states, omega and phi, so if two pure states, there should be a reversible transformation that maps one to the other. You can bring every pure state to every other. Now this is, I guess, very natural because you would say, well, somehow if I have something like reversible time evolution in physics, or if I build a circuit on a quantum computer, then I can exhaust the full state space. I can go from any state to any other pure state. It's definitely true in quantum theory and in classical probability theory. And you can also think of composing two of these transformations. So you have a group of these transformations. So this brings in mathematically the power of group theory into the framework. And for that to work, you actually get some sort of symmetry in your state space. For the quantum bit, obviously you can take it and you can rotate your Bloch ball. That works very nicely. Or if your state space would be a square, then your pure states would be the corners and you can rotate it by 90 degrees. So that also satisfies the postulate. But in the middle here, you would have a state space that's not symmetric enough. There would not be any transformation, any symmetry that maps the one pure state to that other pure state here, for example. So somehow this brings in some symmetry. There's a second property that was already mentioned in the previous talk, which is called tomographic locality. And this is all about composing systems. So what does that do? Well, think of two physicists, Alice and Bob, and they have a certain task. So they are given a state. Think of an entangled quantum state omega, and say they have many copies of that state. The task is they have to determine that state. They want to know what that state is by measurement. It's something like tomography. You do measurements, many of them, and then you get a description of omega. And now what's true, quantumly and classically, is that they can always do that locally. They just do measurements on their half of the state in their local laboratories, and then talk on the telephone and talk each other and tell them the results. They do not have to make some kind of global measurement or meet in the middle and get a hold of the full state. And that's what tomographic locality means. Basically, it says that every state, like this omega here, of a composite system should be completely characterized by the correlations of measurements on the individual components. So from a more mathematical perspective, here's what you also can say. You could say, well, at first, if I just take the framework so far, and if I have two state spaces A and B, omega A and omega B, there are always infinitely many ways to compose them into a bigger state space AB. I just maybe want a few constraints here. Maybe there should be something like product states, which means I can identically prepare a state on A and independently a state on B. I want to be able to do independent measurement, but that's everything. That still leaves many possibilities open. Now, what tomographic locality gives you is basically something like a tensor product. It tells you that if you look at these vector spaces that carry the states, then the vector space of AB must just be the tensor product of the vector space of A and the vector space of B. That's another reformulation of tomographic locality. I think it's also mathematically very natural to expect something like that. Now here's the conjecture that I will discuss in the following. The conjecture tells basically that these two things give you quantum theory, period. So in more detail, if we have some composite state space AB, omega AB, which is a locally tomographic composite of some omega A and some omega B, and if A and B and AB, all the three state spaces, satisfy this reversibility axiom, every pure state goes to every other reversibly. And also, if there is at least one transformation on AB, which is not a product transformation, then you get a quantum state space or a subset of quantum theory. Maybe you get classical physics, for example, which would be a subspace of a quantum state space. Question?
So reversibility means specifically that the group of unitary linear transformations acts transitively, or some group?
No, they're some group. Yeah, you can think of a weird state space. I had the square, for example. Yeah, and this is really a state space that has 4 pure states, the corners. And the reversible transformations could be the dihedral group where you have reflection, 90-degree rotation, and that would map every one of the 4 to every other one. That would be fine. And that's not quantum, and there are no unitaries or anything.
So you want so a subspace like a cone in a real vector space, which has a group of like a transitive group action on this set of pure states. Or whatever.
Exactly. Yeah. Yeah, you have a cone, you have the cone base, and the extremal points of the cone base, you act transitively on them by a group. That's basically it. Yeah. And now this property here, what this tells you is that you have the two systems, and you have some reversible map, maybe a circuit or time evolution. And what you do not want is that all that can happen in physics is just A evolves independently of B. There should be at least one transformation which makes the systems talk to each other. Okay, why is this interesting? Well, so first of all, if the conjecture is true, I would say that it gives a very, very nice and clear idea or answer to the question, why do we have quantum theory in physics? Because somehow reversibility is very important in physics, tomographic locality is very well motivated, and if that brings you down to quantum theory, then it's a nice understanding. But actually, I hope the conjecture is wrong. This would be much more interesting. That would be interesting in physics, mathematics, and computer science, I think. Because if it's wrong, then you would have these other theories which are not quantum, but have these nice properties. So it's physically interesting because that could describe some possible new physics or alternative physics. So you could try to go out and test for it. Mathematically would be interesting because you have these state spaces that have this nice interplay between convex geometry, group theory, and multilinear algebra. And in computer science, you might want to take these other theories and contrast them to quantum computation and see what their computational power would be. So that would be really nice if we could disprove this conjecture here and really construct some non-quantum theory of that kind. Okay, now what about the conjecture? Well, here's some evidence that the conjecture is true, unfortunately, which nevertheless I think is in itself interesting. So let's look at this one example for when the conjecture is true. So among all these state spaces that I talked about, there are ones that are kind of very naturally describing bits or two-level systems with binary alternatives. And these are the ones which have a Euclidean ball as a state space. For example, the quantum bit is one example with a Bloch ball. But actually, the classical bit is also a ball, so it's like a one-dimensional ball. And you can always distinguish the North Pole, for example, perfectly from the South Pole, but not more. And these state spaces showed up in many places in physics. For example, if you do quantum theory over the reals, or the quaternions or the octonions, then you'll find also these Bloch balls, but of dimensions 2 and 5 and 9, for example. And so what did we do in this paper here now? Well, we said, suppose we don't have only one of these bits, but we've got 2 of these bits. And both are described by one of these ball state spaces. Now, let's actually, as in the conjecture, assume that they are composed in a tomographically local way, and there's reversibility for AB and AB. And let's see what we can get. So the first thing that you find is if you want reversibility, then you have this transitivity property, so every pure state can go to every other. This means that the group of reversible transformations on one of the balls must be one which is transitive on the ball. So you can look at what groups are transitive on the ball, and then you find this list here in the literature. So for example, the rotation group is transitive on the ball, but there are other groups that are also transitive on the ball, and you can look at all of them. And you can make one additional assumption that we had to do here, namely, whatever you can do on AB, so every transformation on AB, this group is actually connected group, which is physically reasonable. You think can do nothing, and you can do a little bit more than nothing, and so on. So that would be a Lie group, a connected group. And if you make these assumptions that I've again listed here, then you can just prove the following theorem. So among all dimensions of the Bloch balls and all transitive groups on one of the balls, there are only two possibilities. First, you have a trivial thing where the group of transformation is just the product of the local groups. This would mean that you do something on A, and independently you do something on B, and that's all you can do. And then there's the other case, which works only in dimension 3, and only for the group SO3. And it gives you that the global group must be the unitary group of 4 elements, and the state space of AB must be 2-qubit quantum state space. That's the only other possibility. So in particular, if you ask that these two balls talk to each other continuously reversibly, then this is only possible if they are 3-dimensional balls and you have standard complex 2-qubit quantum theory. Yeah?
Swap them? Does that not count?
Yes, you can swap them, but the swap would then not be in the connected component of the identity. Yeah, good point. Mm-hmm. Yeah. So yeah. Okay, so how do we prove that? Just a little sketch. Well, we think, suppose we have some generator on AB that generates some transformation. We have no idea what that is, what that looks like, some linear thing. But then since we have a Lie algebra, we can use all these Lie algebra properties and do some local rotations, integrate over them, and this way construct some simpler Lie algebra elements. Then we take these simpler Lie algebra elements and see if they preserve positivity of probabilities. And by this, what we do here is we look at a circuit or a transformation. We prepare two local states. Then we let it evolve a little bit according to this generator, and we do local measurements. And we do it in a way such that for time 0, when there's nothing happening in between here, the probability is 0. And since probability must be positive, we kind of get that this probability here must be at a local minimum for 0. And then you can get constraints on all these elements. And it shows you that if the dimension is not 3, then all the generators that you have must be non-interacting, like the sum of two Hamiltonians, basically. Okay, so that's one thing. But now, so far we have looked at pairs of balls. What about more of them? So obviously, in quantum theory, we know that looking at pairs is enough because we have this nice property here on the circuit diagram. If we have 3 qubits and we have a transformation, then we can decompose it into transformations on pairs only. And that's why looking at pairs is enough. But you may ask, well, maybe this is just not true in many other interesting theories that are out there. So, and indeed, Czeslaw Bruckner and Borivoj Dakic had out this interesting paper where they conjectured that if we go beyond pairs, but say to 3 or 4 systems, then we get theories beyond quantum theory, which satisfy local tomography and reversibility, but do not satisfy this circuit property here. So that would mean, for example, that you have 3 balls, maybe they are 4-dimensional, and they interact in triples, but they never interact in pairs. So you put 2 of them together, nothing happens. You put the third, and suddenly you have all these possibilities showing up. They actually conjecture that you have D balls, and you have D minus 1 of them, then you can get a nice interacting theory. Unfortunately, so this is now work with Marius Krum, with my student. This seems to be wrong. At least we checked a few of these cases. So what we found so far is the following. So if the ball dimension is either 5 or 7 or 9 or 11 and so on, and if you have at least 2 of these balls, maybe 3 or 4 or 5, and the local group is just a rotation group, then there is still is no nice state space which has tomographically local interaction, unfortunately. But we don't know what's happening for the even dimensions or for the other groups. But at least this proves at least part of Bruckner's and Dakic's conjecture. Okay, so just to sum up, what I've done here is I've given you a conjecture about local tomography and reversibility implying quantumness, basically. I explained to you that counterexamples to that would be really interesting. They would be interesting for physics, mathematics, and computer science. but we don't know any of these counterexamples yet. There's certain evidence for this conjecture, namely if you take pairs of these Bloch ball state spaces, then they can only interact reversibly in this framework if the dimension is 3, and you have exactly the quantum state space. Now, our hope for counterexamples is to have more of these balls. And it won't be a counterexample, but maybe generalize this from 2 to n systems, make the same conjecture. Maybe then you find counterexamples here, but turns out that this is probably my student kills these now. Yeah, unfortunately. Yeah, so this conjecture still stands. Okay, thanks for your attention.
So we are pressed for time, but if there are pressing questions. Yes, Anthony.
So suppose the conjecture is true. So it would be a very striking thing, but would we understand, in a mathematical sense, I suppose it makes quantum mechanics inevitable, but conceptually it's not so clear, is it? Why should reversibility be a sort of self-evident thing?
You would say, maybe from a physics point of view, you could say there is a corner of physics, a regime of physics, where we expect reversibility to hold, where we have time evolution in the usual sense, and then this is very natural. But there might be other regimes in physics, maybe the regime of quantum gravity, where there's nothing like time evolution in the usual sense, and then you maybe wouldn't expect to find that. And indeed, there is now this work on almost quantum correlations, which somehow are a bit stronger than quantum correlations, in which people try to tell stories why they might show up in quantum gravity. So that would kind of fit this narrative that once you give up reversibility in time with a continuous time evolution as one of the ingredients, that this is the key to actually go beyond quantum theory. That's speculation, but maybe that could be the way things maybe are.
Okay, so let's thank Markus again.